Hey, it's Mr. K doing a video for AP Physics 2, and we are going to talk about magnetic induction of current. Yeah, what the flux? So, first off, let's talk about what is flux. This thing called flux is let's say you got like an open door and you have people walk through it. That's an influx. Or you have a pipe with some water flowing through it. There's an influx of water through the pipe. Flux is this word that talks about like how much stuff is going through a certain area. So we can have electric field with a certain amount of flux with electric field. That would be like E times A, the electric field times the area that it would go to. That would be electric flux. Little symbol for flux is this I with this circle in the middle of it. And we have this other one, which would be magnetic field times A, the area that they're going through. And that's also going to be the I with the circle around it, or through it. So this idea of flux is how much stuff could be going through a given area. And really, the angle matters too, because I can take like a fan and put it right in front of somebody and point that fan straight at their face like I usually do, and that's like maximum flux. But if you were to rotate that fan a little bit, that's like less flux. Or if you have an open window in your house and you have wind going straight at that window, that's maximum flux. But if you had the wind just going by the house, you wouldn't have any flux through the window. I mean, you might have a difference in pressure, yeah, true, but there would be essentially zero flux through that window if the air was going, past the window and the window was like this. Whereas if the window was like this, the air is hitting it, that would be maximum flux. So this idea of flux, usually you're going to see a cosine theta here along with it. And what that just means is that, hey, usually we give you that angle to where if you take the cosine theta of that angle, it's going to give you that component of the field that is in that, going straight through that area. And so we can say, all right, here's this magnetic field, and maybe this is my area. It's going to be a nice circle, and the area of a circle is pi r squared. So if I were to put this circle like right here, that would be like maximum flux through this area. But if I were to turn it like this, that would be zero flux through that area because it's just going on either side of it. So a better way to show it would be like this. If I were to go, then my shadow, my field lines go just right around above and below. But if I did this, let's say if I did this, then you could see that there is a component that would be going normal to that surface area. And that would be the component that we're looking for flux. So right now we're going to focus on magnetic field flux. With Gauss's law, we would figure out the electric field flux. But right now we're on magnetic field, so let's go ahead and stick with that. And so the main focus of this is going to be Lenz's law and Faraday's law. So it turns out if you were to change a magnetic field near some conductor or some copper wire or something, something that can conduct. If you were to change the magnetic field in this guy, then you would end up setting up some current that would try to counter that change. And we're going to start using right-hand rule with all this stuff. So Lenz's law says, hey, you got this changing of the magnetic field. There's going to be something that's set up to try to counter that change in flux. Faraday's law says, yeah, it's going to produce some amount of voltage to produce a current. And the strength of that is based on how much flux you changed in the time that you took to change it. So Lenz's law is going to tell us the direction. Faraday's law is going to tell us how much. Really, though, the main concern would be this. What is our change in our magnetic field flux divided by a certain change in time? And then this change in flux over change in time is going to give us some EMF, or in other words, some kind of voltage. All right, it's going to give some reason for this current to want to flow. And the direction of the current is going to set up a counter-magnetic field to counter the change that we just introduced. So the best way that I can show you is, let's say like this. If we had this magnetic field and I had this can lid thing, imagine that I cut out the inside of this. And I wonder if I can have a better lid than this. Yeah, nothing in the vicinity. So imagine that this is just a ring of wire. And so here's my ring of wire. I go over here, I go ha 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 ha, ha, and I place it right there. Well, what would happen to this ring of wire? And the answer is absolutely nothing, because I introduced no change in the flux to this wire. But if I were to do this and say, okay, hey, we are down here, and right now, what is our current flux through this wire? It's 0. If I were to move it up here, suddenly now I do have flux, which would be the magnetic field, whatever the strength would be, times the area that this let's say this is just a ring of wire, would be. And so yes, I now have introduced some amount of flux to that wire. And depending upon how quickly I did it, it would produce a voltage or a potential difference or an electromotive force to get this current flowing in one direction or the other. And the trick would be to figure out which direction that is. So let's, again, imagine this had no flux. Now it has a bunch of flux in the rightwards direction. And Lenz's law would state that if we introduced all this magnetic field or flux in that direction, the original flux was nothing, and we introduced all this flux to the right, so there's going to be a current set up to counter that flux, and that current is going to want to create magnetic field that goes to the left to try to get it back to the state that it was in. So the way that we would do that is we would either create a current that is flowing this way, either like this clockwise direction or this counterclockwise direction, to counter the introduction of the flux of magnetic field that just happened. Okay, it takes a little bit to think about. We're going to go through this several times. So I have no flux. I now have flux. The flux is to the right. I got to counter it with some kind of magnetic field that goes to the left. And the best way to get magnetic field that goes to the left would be through some kind of current that either flows clockwise or counterclockwise from this direction. And I think that if I were to tilt it this way, we need magnetic field that goes that way, because that would be countering the direction that we just introduced to it. So I need magnetic field that goes this way. Well, let's see. If I were to take my closed right-hand rule, if current were to flow clockwise in this conductor, then that would produce, yep, if I were to grab onto the bottom of this here, if current were flowing to the left at the bottom, grab onto it, my thumb points to the left, my fingers would curl inwards, that would give me a magnetic field that would be counter to whatever this is. So if I did this, then I would set up a current that would flow in this direction. Okay? Now, it wouldn't flow for that long because there's probably some resistance in this conductor, and eventually the normal state would be this amount of flux. And so now there is no need for a current there. There's no need for a countermagnetic field. This is the natural state. Well, what if I did this? Well, now if I went this wire was used to having flux in this direction, to the right, let's say in the direction of the pen. That's where it used to have flux. It wants that back. And in order to get that flux back in that direction, it would have to create a current in the other way. Okay, if I were on the right side, put my thumb up there, my fingers would curl back through, pointing towards us at the moment, such that my magnetic field lines would try to replace what it had just lost. Okay, so let's run through it. Try it again. This is one of those things that you got to run through for a while. Okay, let's see. If we had well, actually, let's just use it. Let's just use this. There you go. Let's just say we have this conductive wire here, and we have a magnet. Let's say this is the magnet, and we said, all right, let's say that this is the North Pole. If this is the North Pole, that means that magnetic field lines are going out of this North Pole. Here's a conductive loop of charge, or conductive ring. The current state is the flux is 0. If I were to bring this North Pole of the magnet right here, that means now I all of a sudden have all these field lines going into the page. Okay? But the original state was nothing. So we have just introduced magnetic field going into the page due to our north pole that we just brought there. Well, to counter it, this conductive loop is going to try to create its own magnetic field going out of the page. So for every 1, 2, 3, 4, 5, we should have 1, 2, 3, 4, 5. It's an attempt to counter whatever gain and flux it just got. The only way we can do that is with current that either flows counterclockwise or clockwise. And so if I were to take a look, I need magnetic field to come out of the page at the moment. And so the only way I'm going to do that is if my current flowed counterclockwise. And so I would take my thumb, point it in the direction of that current, my fingers would curl around, and they'd come out of the page on the inside of this. And so for that moment, whenever I introduce that change in flux, depending upon how fast I did it, I would introduce a voltage to this conductive loop that would give this current a reason to move. This current moves, moving charge, moving current, it produces magnetic field, and that magnetic field would try to counter the flux that it just got. All right. Same thing if I were to take this loop, if I were to make it all of a sudden bigger, or if I were to all of a sudden make it smaller in the vicinity of this magnetic field, I would also gain some kind of voltage because I would be changing the flux, because not only does flux depend on the field, it also depends on the area. So if I were to change the area, make it small, make it big, I would get a induced current here. Classic problem that I like to show is, what if we had a little cart, and this cart was itself a big loop of charge, or a big conductive loop, and let's say we had this region of space where you had this magnetic field that goes into the page. Okay, and so this car is going to go to the right. Right, it has velocity to the right. And so this car would begin to enter this region where there is magnetic field. And when it entered that region of magnetic field, the question is, what would happen to it? And so the first thing that we'd have to look at is, well, what was the flux like in the first place? And the flux for this car would be nothing. There would be no magnetic field going through it. As it entered this region of magnetic field that goes into the page, well, this is not natural to it. The natural state was nothing. And so as we are introducing magnetic field lines going into the page, this car is going to try to create a magnetic field that goes out of the page. And again, the only way to do that is to have current that flows in this direction. So no matter where you grab, if I were to grab at the bottom, my fingers curl out of the page. If I were to grab on the right side, my fingers curl out of the page. If I grabbed on top, the fingers curl out of the page. And so as this car was entering this region of magnetic field, then I would have this current flowing counterclockwise. Interestingly, energy can't be created or destroyed, it just kind of changes forms. How did we get motion to this current? Well, if we look at this current flows upwards. It's in a magnetic field that points into the page. There would be a force on this car pointed backwards. And so this car would actually slow down. And that slowing, that reduction of kinetic energy, as this thing entered and it had this changing of flux to give the motion of the current, that current gains its energy from the loss of speed of this car. Okay? Now, when this car is all the way in this region of magnetic field, well, nothing happens because there is no changing of flux anymore. So again, we had nothing, now we have something. In the transition from nothing to something, there's a change in flux. Therefore, we get some voltage, some reason for the current to move. As we're in it, constant fields, there's no reason for us to have voltage, there is no changing flux. Now at the very last part, as our car began to exit this region, okay, now we have that opposite effect where it had a bunch of magnetic field lines going into the page. Now it's losing it. And so we need to try to get it back. And to get it back, we are going to have magnetic field lines into the page. So we're going to have current that goes exactly opposite as it did in the first place. And so While my car enters this region of magnetic field, we have current flowing counterclockwise. As my car leaves it, we're going to have current flowing clockwise. And again, as we leave it, because my current is induced, I have upwards current, I've got field into the page, I'm going to have force on this car in the backwards direction, again slowing this car down because you can't create this energy from nothing. So it takes a bit of practice. We'll practice it a lot in class, but definitely try to watch the video again to get a little better grasp on what I was saying. Lenz's law, Faraday's law, it's going to be the induction of current based on changing magnetic field. The key word is flux. We should probably make a shirt of that, like what the flux, or who I give no flux. No flux given. That's pretty good. All right, that'll end this one. See ya.